Privilege to be the chairperson of this afternoon session. Because two of my close friends, Joseph and Mike, are going to be the speakers. I learned about Joseph after he published his first paper in Science with a very intriguing experiment which he demonstrated as a vortex by just, let's say, with an evaporator, and you rotate the solution in one direction, you get one kind of chirality, and then if you do it in the other, you get another kind of chirality. This was a very intriguing experiment. But more recently, I know that he was very much interested in this field of sodium chloride, and I know about two exchanges of letters in chemistry in the European Journal. So the last one, if you look in the last issue of 2007, you'll see there was a big discussion, very long discussion between Joseph and Donna. Unfortunately, Donna came here to continue the discussion about the question of the symmetry breaking by the Viedma reaction of sodium chloride. I think that today, Joseph, you're going to tell us a little bit more about it.
Before to begin, perhaps to say that people trying to steer in one direction or the other direction must take into account that you need a size limit in your particles, and then a chiral shape in the particles. And then when you have round particles and so on, there is no chance to observe this effect. But when you have something as helix and something and in the nanometer size, then you should try to do it, but not with round particles, because in this case there is no chance to observe anything. Well, now I will present something that is my reflections just to understand in chemical terms what the physical, chemical physics and so on describes in spontaneous mirror symmetry breaking process, and I suppose that in some aspects it could be controversial, the presentation here, but I think we will have here no much so strong discussion as we have in our group between the people, and that all the things that you can discuss with me, there is already discussion here in our department. Well, it is the start here that is when we have an achiral component dissolution crystallizing in an antiomer conglomerate racemate. Thus, an enantiomeric excess can arise from kinetically controlled crystallization. That is, of course, null. And then there are the papers of Condepudi about the stirred crystallization leads to an enantiomeric excess. Principally, the interpretation is secondary nucleation. However, probably secondary nucleation plays a role here, but when you look exactly in the condition of Condepudi papers, they are not crystallizations made in a first parent crystals. They are crystallization made in relative high excess in oversaturated solution mostly. And then at this point, I think that these results are related probably in some part with Viedma experiments. And then the experience says, I am not a crystallograph, that any racemic or scalemic crystal mixture in equilibrium with a saturated solution maintains his enantiomeric excess. That is an accepted fact. But what the Viedma experiment says is that the same system in the same conditions, but strong perturbated by milling, ends in a nice enantiomeric excess value independent of the initial composition. That is a paradox, and both things cannot be related. They are one of both. One of these must be wrong, because it is when was interested in this, and we was looking in the literature what we have in the solution to perform so a simple Gibbs thermodynamic analysis, and that is the first question if enantiomers are the same compound or different compounds, and of two enantiopure phases are they were already technograms at the beginning of the Ruhr phase in Germany, one talk have made in a presentation in Berlin, and that this presentation is right up here, and he dedicates a good part of the presentation of his considerations to analyze if chiral compounds are different compounds or not, the phases or not. And then in the case of the tartrate cells, that is the point, we have water in the solution, we have one or two components or one or two phases, and depending on this one, you can apply the rule of phase of one of these solutions, but it is accepted that it is taken this one, and because they say that enantiomers or chiral compounds are identical from a thermodynamic point of view. And then he analyzed the case of sodium chloride and make it similar, that is the same case of sodium chloride is in the case of a fast respiration compound in the solution. It is, he's speaking this, that is 9.4 or 2, no? It was. And he speak already about Walden racemization of enantiomeric compounds in the solution, that I wonder what person could in this time to understand really what this one of paper, because he really speak about the racemization of a carbon atom in the solution. And in these cases, he applied that it seems that the rule phase don't apply, because in this case of here, the system must show a behavior that don't agree with the experimental behavior. It must be this one here, because enantiomers are identical from a thermodynamic point of view. And then it is the case of this one here. And then 1 year later, Ruth Beckscheider from Vienna write already a paper discussing this was about if they are the reasons that apparently the real phase cannot be applied to an enantiomer. And then immediately there is an answer from Berlin, Herbig, saying that is the reason. They agree that are thermically identical, but the question is that Beckscheider say that cannot apply at the real phase to an antipure object. And Big say that is there. That is another answer from the Herbig, and an answer of the Herbig. And then the tone of the answers were increasing in the debate. It was increasing, there were some personal things already here. Probably one is Berlin, the other was Vienna. In this time they was separated German countries, and it is another question. And I think I missed two more questions of this one. Well, 100 years later, we have occurred to publish the same question here, and they are the same phase, they are thermodynamically identical or not. And then Professor Blackmont had answered to our article, and we have also answered to this one, and he has answered this one. And then I promised that we will write anything more about this one in this one. But I hope that we don't need to wait 100 years to clear the situation if they are. Well, and then I will speak about this one. Well, enantiomorphic crystals cannot be thermodynamic identical when surface interaction occurs. When we have a melting point diagram of this one, in the case of total immiscibility, but on the complex we have this one, and thus this indicates us that they are different thermodynamically. And that is the case, a more rare case of partial miscibility, but it means that the two enantiomorphic phases are not thermodynamically identical. The question here is, what is the reason? this morning the people had already agreed about this, that is a single crystal with the less surface area is the state of minimum free energy. That is a single crystal, of course, but in the case of many crystals, when we compare the total energy, including the surface interaction of L and the crystal, that is, including the surface interactions, then it is also more stable, thermodynamically more stable, the 100% of one crystal. It is not necessary to have the crystal. The question is if you take into account the surface energy or not. When you don't take into account the surface energy, they are thermodynamically identical. When they have to be taken into account, then they are different. And then, when you don't take into account the surface interest, they are two components, two phases in the system. So when you take the surface energy, then there is surface interaction, that is the case, and then probably the system must evolve to, for example, to reduce one of the phases and to have only one of the phases. And that is our explanation, or basic explanation of the Birnbaum experiment. And then, when we have a stagnant or gentle stirred solution, we have this case here, and then the mixture in the solution is stable, depending if it is racemic or scalemic. And when we are surface recognition, with some weight here, then the system has this one and must evolve to homochirality, or practical homochirality from the racemics. Well, I present now that is the solution and stability analysis of reaction networks showing spontaneous symmetry breaking. Understanding spontaneous symmetry breaking of the process that can attain a chiral final state by thermodynamic control. It is not by kinetic control, but thermodynamic control. That is the mathematical analysis of this. It is made by David Hoffberg. It is a pity that he come here, because I will need to defend me some other one, and not me alone here. But we have to simply, that is the chemical digits, so that the chemical interpretation of these results. I present here now the more simple model, the limited enantioselectivity model. We have this track reaction, the enantioselectivity catalysis, and the necessary state of leading to the critical symmetry breaking, that is the non-selectivity catalysis. That is the equations that we write the chemists of the kinetical equations. As the physics side, the mean field theory, they take into account diffusions and noise. The here are not taken into account, they are taken away. And we have analyzed an open system and a closed system. But they have performance, that is the no dimensionalization of these equations, defining two parameters. The G parameter, that is the ratio between the backward rate constant of the enantioselective catalysis and the non-enantioselective catalysis, and the W parameter, that is the ratio between the forward rate constant of the non-enantioselective catalysis and the enantioselective catalysis. And in the closed systems, the parameters are this one, and that is this here too. And then they define two new variables to the system. That is the total chiral matter, Xi, and the different chiral matter, so that the eta, the enantiomeric excess fraction, is simply this relation here. And they solved this one for the open systems, and they found three solutions: a non-physical solution, that is the zero solution; the zero solution, that is the racemic solution, that is the total chiral matter, that is the enantiomeric excess, zero; and the two chiral solutions, one is the total chiral matter and two is zero. enantiomeric excess corresponding to this one. And in the closed system, they find two racemic solutions. One is unphysical because he gives negative total chiral matter. It is have only sense the positive racemic solution, and two chiral solutions, and an enantiomeric excess at normal concentration values, that is not very diluted value. It is the same enantiomeric excess in the open system and in the closed system. And then the stability analysis of the solutions lead to the following one. Thus, when we have the G parameter bigger than 1, that is the relation between this one potential and here. The racemic solution is the only stable solution, and in addition, the racemic solution is also the stable solution of the systems in the case that the G parameter is bigger than the G critical parameter defined by this expression here and this expression here. Is this value. It means that in fact the results indicate that you can define the systems by the parameter G and the parameter W. It is the ratio in the forward reactions for the enantio and the non-enantio selective catalysis and the backward reactions. And the chiral solutions are only stable, and they are only the stable solutions in the case that the G parameter is smaller than 1, and that is a necessary but not sufficient condition, and when the G parameter is smaller than the G critical value. You can define the situation between the two. Look, that you have defined the solutions here only with Q2, Q-2, Q3, and Q-3, with these two parameters here. And then when you are here, you have a chiral solution depending on the values, on the ratio of these values. So when you are here, you have the racemic. But the question here is to interpret this one in chemical terms, because it is possible to get a G value smaller than 1, and the answer is probably it is very difficult. Because when we say that this is the enantioselective catalysis, much faster than the non-enantioselective catalysis, then the backward reaction must be also faster the non-enantioselective catalysis than this one here. That means that the ratio of this kind, it's simply the reaction, free energy rate of the reaction. It means that in all the strike reactions, the enantioselective catalysis, the non-enantioselective catalysis must have this pressure here, and then the question is that the G value is always greater than 1, and then it means that it will be only possible the racemic solution. And when we think in systems where the non-enantioselective catalysis will be faster than will be better than the enantioselective catalysis, it's also not possible to get a chiral solution, because this W value will be smaller than 1, and then the G critical value will be smaller than 0, and then it will be not possible. Then apparently what occurs is that spontaneous mirror symmetry breaking cannot occur, but can occur when it is fulfill the conditions of the chiral solution. And this is the normal case when the end products are the same on the three manifolds, the two homochiral manifolds and the racemic manifold. But when we imagine simply, before to consider in detail the Frank model, simply that we have that the final products are not independent one to another, but they can interact one to another. In the final state, when we apply here a an additional standard free energy of interactions, for example, forming a dimer or forming an aggregate or something else, then this change here, and when the condition don't meet, we have the racemic condition, but when this condition meets that this J is smaller than 1, is smaller than the J critical, then we have the chiral solutions as the only solutions of the system. And when we look here, it is simple but curious that when this difference of interactions, the heterochiral interactions or homochiral interactions, take the value that is smaller than this difference here, then the system is not stable, and you go for the racemic solution to the chiral solution. That is simply when this amount of free energy here is here. We are considering here the final state. We are not looking at the evolution from the initial to the final state. We are analyzing the final state. It means that the rates are depending on the free energy, are expressed as the free energy. There is also free energy, and here they are included or mixing free energies, entropies, and so on. And so on. And then when we said, well, the interactions, but these interactions are enough to produce this one. It is, they are, the energy necessary is very big or very low. And then we can make simply this one, look for a specific G value. What is the G value necessary when that is, what is the energy necessary to make equal the G value to the G critical value. And that's what we see here. It is something curious. It depends of the statistic of the available reactions. That is when the P3 value is the K2 value is 3 times the K3 value. Look at this, this is the minimum, the necessary energy to go to the chiral solution is the best one. That is a quite different approach for a synthetic chemist, trying to obtain chiral induction, because the important thing here is to obtain the bigger difference between this one and here. The chiral symmetry breaking is obtained as this one. The value here is only 5.5 kilojoules per mole. It means that is the spectral value that can be attained by dimerization in exclusion and so on. When the homochiral interactions are better than the heterochiral ones. Because normally the current case is that the racemic centrosymmetric interactions are more stable than the homochiral. And then it is this one. And then when we look at these values here, what occurs with the enantiomeric excess, from a mathematical point of view, homochirality is not possible, but you see that you can obtain values of the enantiomeric excess fraction near to 1 for all these values here. They are different W values, this one here, and then here it is of advantage to have difference in this value because the increase of enantiomeric excess is better when K2 is much bigger than K3. And here then it is the values obtained, and then we apply reasonable rate constants for the addition that is taken from my Noyori paper on the addition of the alkyl sinks to aldehydes, and that is a system with a very good catalytic value. The strike reaction is very slow, the catalytic reaction is good, and the non-catalytic, the enantioselective catalysis, the non-enantioselective catalysis, they are relatively different, but it is as it have a value from a chemical point of view, or reasonable values for a chemical reaction. And then here it is clear that it don't depend on the reaction free energy. There is no dependence of the systems if you obtain the Chiral solution or not. And then here it is the values that you obtain in the Chiral solutions, and here they are the enantiomeric excess and the corresponding free energy stabilization of the homochiral interactions in respect to the heterochiral ones. Here they are not so good autocatalysis than here, but also similar, and you see that already about minus 11 or kilojoules per mole, the enantiomeric excess is very near to 1. But here, in the type of solution and in the enantiomeric excess, there is no influence of the reaction free energy, but of course they have a significance in some other one that we will take now in the next slide, that is on the time to achieve the final state. Then, in conclusion, that we need is chiral recognition, that we need homochiral interactions preferred to heterochiral ones. And when you look in the examples in the literature, you see that the packing of this type of these compounds are the compounds that you can find in the literature giving conglomerates instead of racemic crystals as the most stable ones. And the structure are similar. Here can be a hydroxyl group or an amino group. Here you can have a carbonyl group or an amino group. And the structure of this substance are very similar to the reported one recently by Sogoeva, and also recently they have some similarities with the SOI reaction. It means we can take as reference the compounds given crystal conglomerates to infer if in the solution dimerization or autocatalysis will be the homochiral interactions better than the heterochiral ones. It must be reduced to a specific structure of organic compounds, and then the third condition is that you need to have this interaction here able to compensate the difference of energy between the transition energy between the enantioselective and the non-enantioselective catalysis. Well, here what is the role of the reaction free energy to attain the final state, and that must be performed from another way, and that is simply take the numerical simulation of the evolution of the system. I present here only the closed system. I can speak about the open systems if you are interested later, but the results are more or less the same. And then, in the racemic solution case, when we take this typical sample here that corresponds to this K1, K2, K3, it comes -1 and -3. And -2 are taken from the expression here, this difference here. And we look at the evolution of the systems when this difference here are benign. Irreversible reactions from the point of view of synthetic chemist, or to the case of low exergonic reactions, as for example an aldolic condensation. And in all these cases here, the important time to achieve it is the induction time before there is a concentration that the autocatalysis is manifested, and then it takes in 1 second or 2 seconds you go to the final state. In the chiral solution case, we have made these simulations here. That is the same case as before, only that we have changed the K-2 to give G values of 0.7 and 0.5. No, sorry, 0.05. Here and also for this actual standard. Then to make the simulation in the lack of stochastic simulation and diffusion simulation, noise simulations as they are performing now the Madrid people, to make this numeric simulation, it is necessary to take an initial numeric access, because in other case it is not possible to do the simulation. And the simulation is made for a total chiral matter of -10 and a numeric access of -8. To attain this concentration here, you need an induction time about 1 second. And please pay attention that this enantiomeric access here, it is approximately 1 order of magnitude below the statistical variation to the racemic state for this concentration here. It is really to start the system, imagining that the statistical difference on the racemic state are enough to go to the symmetry breaking. In fact, you can go 1 order or 2 orders of magnitude lower than this. Unless in our numerical simulation, but that is, of course, there could be calculation artifacts and so on. And the conclusions, in the lack of stochastic behavior of the systems, is that we can look to 2 time scales. And first one, to attain the racemic solution that now is metastable, and a second scale of time that is to attain the final chiral state. Here we have that is logarithmic and concentration and in time, and revolution in red is the chiral compound, in green the L chiral compound, and the initial A compound in as you see that this go here. U remains in the racemic state. That's one time that there is a decrease of the L and an increase of the A. That is, they are really plateaus. They are not increasing. They are really plateaus. This meaning that the systems evolve because the forward reactions are faster, bigger than the backward reactions, evolve to the racemic state. The racemic state is now metastable, but it must take a time before to break, to have the breaking. Here is the variation of the enantiomeric access. You see we have been here, but then in the point that he attained the value of the racemic solution, it tries to decrease more, and then slowly it increases rapidly in the time that you have. More interesting is that the total chiral matter. It is smaller for the racemic smaller for the racemic solutions than for the chiral solutions. And that's for the chemic that is very small. Here is an insert here. It is possible. And that can be observed in any simulations, in open systems and in closed systems. It means that the chiral solution is more stable than the racemic solution in this condition, and it corresponds to a final concentration bigger for the chiral solution than for the racemic solution. Very small, but it is. The question here is to understand in this difference of energy here what it is. I was very interested in the presentation of the Ribo here, because I think that this variation here corresponds to a phase transition of second order, but there is something important here that we are not fully understanding. Well, what is the time to achieve this one, to achieve the change for the racemic solution to the chiral solution? That's when we compare the irreversible synthetical reaction here with an irreversible equation here, then we see that for minus 10 joules per mole, we need in the order of seconds. For 20, we need minutes. For 30, we need already days. For 40, we need weeks. For the reversible case, that is a plus one, we need the age of the universe to observe that the process terrasemizes. It means that the terrasemization is only observed in the case that this one is reversible, not in this one. So that is the best. I think that the limit that we could observe this one in synthetic chemical reaction is about 45 kilojoules per mole. Then you are able to wait some months to look if there is appearing chirality, an scalemic mixture or not. It means that you will observe better the symmetry breaking in synthetic reaction in these cases here, and in the other one, probably you are missing, because you are arriving to the racemic metastable state, and you have not observed it. Well, and then we can add a condition more, a chemical constraint more to this one. It is that to look this one in the laboratory time scale, it is better to have low exergonic reactions than not. Well, coming back to the summarizing this one, it is only when we have this system here, there is no symmetry breaking. We have the strike reaction, the autocatalytic and angioselective reaction. Here there is no symmetry breaking. Here in the system here cannot be symmetry breaking. That is already said some years ago by Professor Kagan and Professor Lagman. When we add a new dynamic network, a new reaction, a new way is here, then the systems increase with this reaction here. And then it will be possible, when the parameters agree with the condition for the chiral solution, that symmetry breaking can occur. And not only this one, when we don't have these steps here of chiral recognition, it is no chance to have the spontaneous symmetry breaking. This condition here is the condition of the Frank condition. This condition here, it is when we have this condition here, it is very improbable, there's probably no chemical sense that we don't have also this condition here. Or when we don't have these conditions here, that we don't have this one, because it must be. The chiral recognition is something that must occur between homochiral and heterochiral ones. Then the kinetic stability analysis, when applied to the final states, stationary or stable or final states, it is the same thing that to make the Gibbs thermodynamic analysis of the system, and in this sense the results agree with our previous, more or less intuitive proposal in chemistry. It is only to stay some moments to say that we have also some results with the Frank model. The Frank model, what we attain with the same mathematical analysis, is also two parameters, but they are more or less similar. Only that is curious here. When you remember, we have this curve here, and here it is possible to attain symmetry breaking also for any values of the critical see? But the possibilities, the range of possibilities of rate constant decrease. And here, for example, when we define the reaction right here, and this independent here, that will be the formation of this one, something that is not taken into account. It is that in the critical parameter that define this one, expressed all the solutions in the free energy of the transition state and the free energy of the reaction. It is a has parameter depending this one and this one. Look, that's the dependencies of this one. It depends of the total sum of this one. It means that this step here. It does not necessarily has to be exorganic. It can be inorganic because the picture is always. One more here. Yes. And this model too, in this more complex model here, we have performed also some of the calculations of the enantiomeric axis, and this is crazy, this one here, because when you change a little the parameters here, you go from the racemic to enantiomeric axis that are near to 1. For example, in this case here, they are exorganic. The mutual inhibition step is exorganic here, is exorganic here. And here it is also depends that the reaction under free energy, it is a little more exorganic here than here, and that suffices to go from the racemic to enantiomeric axis for 90%. It means that in this type of reaction, for example in an aldolic reaction showing spontaneous symmetry breaking of this or whatever, when you change the solvent, you change simply the solvatation of the transition, the activated complex and so on, small changes here of some kilojoules, you go from the racemic solution to the chiral solution and so on. And there is no way to understand what is the reason that rapidly changing a little the experimental conditions, you can get a scalemic phenol mixture or not. I think that's to read the Soga papers in the light of the values here, it is recommended, because it is when you try to find a mechanism, not taking into account the non-linear dynamics of the system, it is very difficult to arrive to conclusions. Let me see now simply that we have three conditions, but not sufficient conditions, that is the chiral recognition between an enantiomer, converged in different thermodynamic species. When there is no chiral recognition, they are thermodynamic identical. And only when homochiral recognition is preferred to center-symmetric heterochiral recognition, in a value enough to a reaction able to attain the omega, it is only possible this one. Homochiral must be preferred to heterochiral. And then there is this preference must achieve a critical value, which is this one. And then when we look in more general consequences of this one, the study of this part here, it is interesting how to arrive to enantiomorphic supramolecular systems, for example, in polypeptides or in the things in amplification of chirality and so on. Thus, the interesting question here, it is perhaps is biological homochirality only by consequence of the thermodynamic stability of the system. This is what we, because I cannot believe that an evolution system must be some more stable than the other one. It cannot be a chance to think that it is only kinetic control here. It must be some thermodynamic stabilization here. And that's when we think that perhaps the homochirality biology is constructed on supramolecular systems where the homochiral interactions are better than the heterochiral interactions, and become here. And then, unless it is already a point here, it is not so simple, this one. When we try to explain what is an enantiomer, as is more than Cristobal, that you must move and so on, you must perform some chiral recognition to identify that is an enantiomer. When you don't perform this one, it is not possible to distinguish if they are identical or not. Chiral recognition is bound to the nature of the optical activity itself. Because without this, and that is related also to quantum chemistry and to the problem of the geometrical structure from the quantum chemistry point of view. And then I think we can have plenty of discussions here. And when I have 5 minutes, I will say only some things about what occurs when we have in such of these systems, when we have the rate constants here are a little different than the rate constant here. That is already known. That these systems must be very sensitive to chiral inductions. And the point that as we are speaking in the last years not of chiral induction in these systems, but in chiral sign selection, because it is not really a chiral induction from the point of view of the chemist, because this difference can be very, very small. And I will show you an example similar to the example proposed in this at the end of this morning. But in the cases that I suppose they are more common than reported, that the people only obtain one of the things. In our case, we have these G aggregates of the tetrasubporphyrin and amphiphilic porphyrin. That perhaps in more than 1,000 experiments, we found always the same chiral signs. Always. And not we, also in Sicilian, and so on. And it seems that in Japan, they have found the other side, but it is not sure. It is not sure, because the people say that they have the other one, but I think so. It is possible. And that the problem is so big that the question is in these aggregates is because the porphyrin is achiral, and then the aggregate is chiral. If there is an artifact, or there is an artifact, for this one, we should invest plenty of time to chiral, to solid CD spectrometry, and then we have observed this one, and that is real, it is true, chiral. That it means that we obtain only this one because there is some undetected chiral contamination. We have found some indications that the quality of water have some influence here, but it could be not demonstrated. In the only possibility, it was this one: to add a chiral contaminant and to look what occurs. And then with the addition of a chiral contaminant, we go to one side and we go to another side. And that, of course, also we need less contaminant in the case, in this case here, than not in this case here, because it is already one undetected. And then we go to the 10 ppb, in ppb a proportion of this one. The explanation of this one, that is water. And the conclusion it is likely impossible to obtain water free of life, or free of debris of life. And then it is the chiral contamination, the archival membranes, and something else. And when you look in the literature, Soret had already reported in the case of sodium chlorate that he obtained only the enantiomorphic, and it is in closed tube and on some degree. But when you look in the literature in the silico tube states, they are modern materials for advanced materials and so on. But if reported in the literature, is they obtain always the same. They must be very sensitive to the, well, they are also anionic. They are also anionic compounds, also in the case of ours. And now I am really finished, and I thank you for your attention.
Well, I think that there are various models that can explain the Viedma experiments. Thermodynamics, kinetics, and I hope that after the lecture of Mike McBride, I think we shall have a very serious discussion about trying to find the differences of the various mechanisms which are proposed for this very, I think, simple-minded experiment. You grind just sodium chloride and then you get this condition. But now we have some room for some questions. Yes, please.
I could follow your mathematical explanation, but I could not some part for physical chemistry explanation. You're considering diamond formation, heterochiral and homochiral diamond formation for explaining why G is not equal to 0, 1.
It is an additional G.
Please see energy, free energy figure for LL or LG or
This one, it is very, yeah, it is very, very small. Try to go. Yes.
You consider diamond formation is, the energy is different from L plus L, D plus D to L plus D.
Yes.
You consider diamond formation.
Yes, diamond, for example, yes.
So why didn't you add diamond in the kinetic model? In your model, regular normal reaction and also chiral catalytic reaction and reverse chiral catalytic reaction. But no, those diamond formations, kinetic model.
No. Well, the diverse formation, it must be a model more complex than the Frank model, of course. But when you are analyzing only the final state, it is simple to add here an additional standard free energy to the aggregation.
So standard free energy, the standard condition. So in standard condition, usually
that is the final state. That is the final state.
Final state.
That is not the evolution. That is the final state.
Final state, but
also the kinetic analysis is on the final state.
Yeah, I think that is the final state. Final state, okay. But standard condition means there's no interaction between particle to particle.
No, it depends. No.
That's why, why this kind of difference as a standard?
No.
Difference than the standard condition.
You can also take into account the standard state of the diamond.
So if there's a diamond, there's another chemical species.
Yes.
There's another chemical species. And
yes. Well, that is a chemical assumption here that they are fast reversible formation of the diamonds.
Yes. So, my question is, why those diamonds are not in the model? Because if diamonds are there, so diamond formation, diamond dissociation also occurs. And if you calculate the stability of the racemic solution, maybe it is stable. I think.
What is stable? The diamond?
Diamond. No. Racemic solution is stable.
No, because you have in this manifold here, you have the racemic here and the other here. Well, that is a situation that is not normal, but not unusual. That is the case that the homochiral interactions are better than the heterochiral. And that is normally not the current case in organics.
But when, homochiral diamond formation and heterochiral diamond formation in the model, and then calculate to obtain maybe racemic solution, homochiral solution, and if you check the stability,
because we have already the help of this one in the Frank model, it is the same conclusion.
Yeah.
The Frank model is the conclusion that you have a chiral recognition. It is the same conclusion that we arrived with the chiral. And the same in auto model and in plot.
The reason why you obtain a homochiral solution is you change.
We don't obtain homochiral solution. We obtain chiral solution.
Chiral solution. But the reason why is you make value difference between K2 over K minus K3 over K minus 3. That's why,
Yes, but this K here of the diamond are much smaller than the other one. They are fast, reversible process of formation.
You think those ions will go directly into diamond?
No. No. Imagine they are hydrogen bonding between the chiral compounds in the solution. Imagining that you have interaction forming by a diamond by hydrogen bonding in the solution, and that this hydrogen bonding between homochiral is better than the heterochiral. And you don't need to include this one because in this case it is order of magnitude of the other one.
Yeah, because there's no diamond in this energy figure.
Here, well, this perhaps is not, but this decrease here is to the interaction, to the aggregation.
Yeah. So you think it is diamond? You think it is diamond? L plus D or L plus L? Those are diamond. So, but there's no diamond in the kinetic model. Only single molecules.
Then there is no symmetry breaking.
Yes, of course.
Then there is no symmetry breaking. It is only in the case that they are additionally interaction. When you don't have interactions, when you don't add the chiral recognition, you can intuitive here to apply this here or not, then it is impossible to get the symmetry breaking. Then the experiment of Soai, it is impossible. The experiment of Pierman, it is impossible, and the reports of Soai should not be accepted. But when this occurs, it is only because there is an interaction, chiral recognition between the compounds, in the formation of it. And you don't need to have irreversible formation of the compounds. It's better that you have simply irreversible fast. Because in other case, it is impossible to have. And all the examples read in the literature, physically, they are implicit, the chiral recognition. Only that they don't say it or they realize it. In the model of this model, it is also the chiral recognition in this computer simulation. Without chiral recognition, it is. In the Pena's paper of Kobe-Irasu that is also implicit, the chiral recognition. Because without chiral recognition, the only final state is the receptor. It is not something new that they say here. It is already implied in all the models describing the symmetry. In all these models, this implies the chiral recognition, because without chiral recognition, the final solution is irreversible.
If I understood you correctly, what you're saying is the contact between heterochiral crystals creates...
In the case of crystallization,
So
yes.
is it possible to perform an experiment where you can, let's say, grind, separate enantiomorphous crystals which are contacted somehow by solution? Because if it is a kinetic process, and this distance between the two aggregates, the two type of crystals, are close enough, then maybe then if it is a thermodynamic control, then you should not observe such kind of transition. When it is a kinetic process, then you know that when you need the formation of the clusters and all this which are playing
Well,
role.
in my opinion, what I am describing here, it is spontaneous symmetry breaking defined as in the thermodynamic field state. Not in this one. I think that the model is good. We can have later a discussion of this one, but I think that to mix in the same model kinetic control and thermodynamic control is not allowed. And they are speaking here, it is the stability of the thing.
The second question that you propose.
But in this case, sure, when there is a possibility to perform the experiment, you are the person to, you have already do it.
Second question, that you made an assumption that by looking on the interaction of the molecules in solution, and they must be also the same type of interaction that you have in the crystalline phase. Now, of outside that are studying nucleation, we know, for example, take acetic acid. Acetic acid, in solution you have these centrosymmetrical dimers, whereas in the crystal you have the catenary motif. And there are many other examples. that people are actually looking in that whether the clusters which are forming a solution are the one which are responsible for the crystal. Like Hooks, for example, he will tell you it is the octamers of serine, but these octamers are not existing in the crystal. So the question, the assumption that you made that the same homochiral, preferred homochiral interaction should also operate in crystal should
yes,
take into account.
it is only
it's not universal.
not universal, but it was one thing that I am working in an organic chemistry department. The people are interested in the synthesis, and then how do you can look for systems looking for this behavior, and then looking for this behavior, it could be an indication the compounds crystallization forming conglomerates. It was my it is going. So it is on the shells, on the design of reactions. And when you look at this type of structures, these ovoidal structures, and this one, that is probably compounds giving conglomerate in state of rest. That is only to try to design and to find reactions looking for symmetry breaking. And the sense of my presentation of the paper that we have submitted is this one. It is in what cases we could have some probabilities to go spontaneous symmetry breaking in synthetic organic reactions. And then this is to look for autocatalysis, of course, and so on. And then when you look at this one. And also these compounds have the opportunity or the possibility to be synthesized by addition for nucleophilic addition to carbon. They are similar. This is what only to present and what type of...
I wanted to make them comment that in principle we can measure these interactions in solution between enantiomers by differential scanning coulometry and some studies along these lines.
I think that the synthetic chemistry are more interested to have reactions than not to look.
The last video today.
There's a break, right?
I think the last, no?